மாமாக்கு முறுக்குதா?
Good evening, guys. Are you able to hear me?
Yes, sir.
Yes, sir.
Okay. So first important question I wanted to ask is, when I check the app, right, if I take the ratio, it is less than 10% of you who has completed the notes. Less than 10% has completed or even worked on what the notes were, worked on the videos that were given last week. May I know what is the reason for it?
Sir, for me, I wasn't able to open the notes, sir. I tried again and again, but I just can't even know.
Okay.
I did
Others?
all
So batch one, especially the last two things I see, till constructive and destructive interference, out of 31, 14 members have submitted. The interference part, none of you have worked. Out of 31 members, 6 members have submitted, and the diffraction part is completely dead. and which is the toughest topic. Out of 31, 4 members have submitted. That shows a clear negligence from your side. I'm telling you, no, that's a clear disrespect for the work that we are doing. Which is definitely, I'm not even happy with any of you. Batch 2 also the same thing, same nonsense. Some of them have not even touched. I made a list of all those things, all the names. You'll be getting a message, okay? I want to talk to you guys about these things. If anybody has doubts on wave optics, they can ask me. I will answer the question only if you have uploaded the notes. If you have not done it, please stay away from asking a question. I'll not clear any doubt. See, with respect to wave optics, according to me, it is done, okay? It is your work. I was actually planning to take some doubts class today based on wave optics, so that I thought you'll work and come and there'll be some difficulty so that I can help you guys. But absolutely nothing from your side. You better struggle. I'm giving you a last warning. Listen to this carefully. I'm telling now, I'll put a message also. Listen, everybody listen to this carefully. I'll give you 2 more days time. By Wednesday evening, I want to see that the gap is completely filled. Okay, and if you guys are going to take the chapter for granted, forget about it. I'm not even going to teach. I'll only conduct class for those who have completed. Others will not even be allowed to sit and sit. I'll not even let you inside. I'm seriously not able to tolerate this kind of a behavior, you being in 12th standard. Write down the next heading. It is dual nature of matter, which is chapter 11. So dual nature of radiation and matter. So the topics that we are going to cover in this chapter are, we will see what is the introduction to this chapter. We will see what is electron emission, photoelectric effect, experimental study of photoelectric effect and the connection between that and the wave theory. Then we'll see the Einstein's photoelectric equation, which is also called as energy quantum of radiation. Then we'll see the particle nature of light, wave nature, and this Davison and Germer experiment. Actually, this part is not there, so we'll only see the outline of it. Listen. So here, if you see dual nature of radiation, when I talk about radiation, I'm talking about light. And when you talk about matter, I'm talking about the subatomic particles. So what are subatomic particles that we know? We know about the electrons, protons, and neutrons, but here the subatomic particle I'm trying to talk about is the electron. Okay? Listen. So from the previous 2 chapters, actually the previous 3 chapters, we know the fact that light has like the basic branch of physics that deals with light is optics. So optics is basically classified into 2 types. What are they? One is called as the ray optics and the second is called as wave optics. Okay. So in ray optics and wave optics, as we are able to understand in this wave nature, right? So we know that light has wave nature, but when I explained about the wave nature, there was a prelude to it. So there was a scientist, Newton, who proposed saying that light had particle nature associated with it. Then the scientist Huygens came to explain that it had wave nature associated with it. So when I talk about the particle nature, the corpuscular theory literally failed. Right. So when it failed, it was understood that light had, so people started believing after the YDSC that light had only wave nature. So in the 20th century, what happened? There was another experiment, that is photoelectric effect, that came into existence, which could be explained only with the particle nature of light. So it is then the conclusion came that light didn't have only wave nature, it also had a particle nature associated with it, and the concept of dual nature came into existence. So that is why the statement starts like this: the true nature of light is difficult to assess. Experiments showed that light exhibited wave-like properties of diffraction and interference. So you cannot explain the concept of diffraction and interference using the particle nature of light. You need to use the wave nature of light to explain it. On the other hand, if you see the other experiment, that is photoelectric effect, which indicates that light had the aspects of particle photon with both energy and momentum. So photoelectric effect was explained using the particle nature of light. Right. From this, the concept of the wave particle duality came into picture. Right. Then what happened? The wave particle duality was extended to particles. So initially what happened? They thought light had wave nature and particle nature associated with it. Then it was understood that nature follows symmetry. If light had particle nature, then particles had wave nature. Okay. So the wave particle duality was further extended to particles as matter waves by a scientist named Louis de Broglie. Okay. So you pronounce it as de Broglie. B-R-O-Y. Generally, you would have learned it as de Broglie, right? It is pronounced as de Broglie. Okay. So his theoretical study on the nature of particles and waves led to the invention of new mechanics of particles called as the quantum mechanics. Okay. So this is the introduction that we need to know. From here onwards, we are going to concentrate on the experimental aspect. So concentrate. The concept that we are going to see is photoelectric effect. So this concept of photoelectric effect is not new to you. Can someone tell me what is this photoelectric effect? If you break it into two parts, photo is derived from light. Electric refers to charge. Right? Having this, what is this effect all about? Tell me. Anybody?
I think when light hits, the electron just leaves, right?
When light hits an atom, so which electron leaves?
The valence electron.
Yes, you talk about the valence electrons. So light is going to supply enough amount of energy for that electron to come out of the nuclear pull. Is that right? So electron
Yes.
will get knocked out. Is that right? So that is one thing. If the electron is getting knocked out, what is going to happen? The atom will get converted to an ion. So ion is basically a charged particle. Right? Electric basically refers to charge, as I told you. Right? 1 minute. Okay. So I hope you're able to understand. So photoelectric emission is basically, it's a phenomenon. It can be felt actually. And for what kind of material will this take place? It will take place only for metals. Why is it happening only for metals? Because metals only have loosely bound outermost electrons. Right. So photoelectric emission is a phenomenon by which a good number of substances emit electrons of radiation such as gamma rays, X-rays, ultraviolet, and even visible light. So this effect was first observed by a scientist named Heinrich Hertz. So this happened in the year 1887 while he was working on some other thing. While he was working on something called as resonance electrical circuits. So it was first observed by him, okay, while working with resonance electrical circuits. And a year later, Hallward, Elster, and Gatel investigated the phenomenon with the same experiment, with a simple experimental arrangement. And this Hallward's experiment is what we are going to try to understand now. Okay. So when you talk about the Hallward's experimental setup to study the photoelectric effect, it is shown below like this. So you take a battery, and that battery is connected through a galvanometer. Okay. Then what is going to happen is the positive end of the battery is connected to a metal called as anode, and the negative end is connected to a cathode. Okay. So on the cathode, if there is a light radiation that is going to fall, then it was observed that there were some charges that were coming out. So basically it consists of an evacuated quartz bulb. Why we are talking about an evacuated one is because if the electrons are coming out, right, we need to ensure that there is only vacuum and no other particles where these electrons are undergoing any collision. So it consists of an evacuated quartz bulb with two zinc plates. One is cathode and the second is anode. Right? Then the plates are connected to a battery and a sensitive galvanometer. So in the absence of any radiation, what happened? In the absence of any radiation incident on the plates, there was no flow of current, and hence there was no deflection that was observed in the galvanometer. So what happened? There is no flow of current, and hence there is no deflection taking place in the galvanometer. But as soon as the electromagnetic radiation, like ultraviolet radiation, is allowed to fall on the plate C, which is connected to the negative terminal of the battery, then what happened is the current started to flow, indicating a deflection in the galvanometer. That current didn't happen because of the flow of charge through the battery. Rather, it happened because the circuit got completed. See, initially the circuit was not completed. There is a gap. There is a gap that is existing here. But the circuit got completed because it was observed that there were some electrons that were getting liberated from this, and these electrons got collected by the anode so that it could complete a loop. When this happens, you can say that current is flowing through the circuit and the galvanometer showed some deflection. But what happened when the same ultraviolet radiation, it was made to fall on plate A, there was no deflection in the galvanometer. So basically what happened, both were made of zinc plates only. But the difference is one of the zinc plates was connected to the negative terminal of the battery and one of the zinc plates was connected to the positive terminal of the battery. But when you did the same experiment by making the light rays fall on the anode, you observed no deflection in the galvanometer. So these observations reveal that the particles emitted by the plate C due to the photoelectric effect are negatively charged. And these particles were found to be electrons. The observed current that was observed in the galvanometer is what is called as photoelectric current. And this photoelectric current is purely due to the concept of flow of electrons. Okay, so this is the basic setup that was done by Hallward. That is why it is called as Hallward's experiment. Okay. So after the study of photoelectric effect by Hallward, scientists J.J. Thomson, Leonard, Richardson, Compton did a series of experiments to study the relation between photoelectric current, intensity of incident radiation, velocity and kinetic energy of the photoelectrons, and their dependence on the wavelength of incident radiation that was used. So what did they try to do? They wanted to study how this photoelectric current, so what do you mean by photoelectric current? The current that is constituted due to the photoelectrons is what is called as photoelectric current, right? So they try to study the relation between the photoelectric current and the intensity of the incident radiation, the velocity with which they came out, the kinetic energy of the photoelectrons, and their dependence on the most important parameter, that is the wavelength of the incident radiation that was used. Is it clear, guys?
Yes, sir.
Right. So from this point onwards, it is very, very, very important. Please make a note. If there is any doubt, get it clarified. Okay. So the first important point is, how will the effect of intensity of incident radiation be on the photoelectric current? So what is the effect of intensity of incident radiation on the photoelectric current is what we are going to see now. Okay. So listen, the same setup, cathode, anode, both are made of zinc plates. So what do you mean by intensity? Suppose I have a wall here, and on that wall, I am flashing a torchlight. Okay. Then there will be some lighting that is falling on the screen. And there will be some brightness that is associated. Right. If I move the torchlight slightly away from the wall, like this, intensity decreases. So here the intensity is more. Basically, what is intensity? The amount of radiation falling per unit area per unit time. Right. So keeping the frequency of the incident radiation constant. So there are certain parameters that are associated with the incident radiation. What are they? One is intensity, and the second is the frequency, and the third most important thing is the potential of anode. Okay, the potential of anode is also kept constant. Now listen to this. When I say the frequency of the incident radiation and the potential difference between the cathode and the anode at constant values, if we vary the intensity of the incident radiation, then the corresponding photoelectric current that is there, no? The photoelectric current is due to whom? The electrons coming out of that zinc plate. So the corresponding photoelectric current is measured using a microammeter, and it was clearly observed that the photoelectric current increased linearly with the intensity of radiation. Means as you keep increasing the intensity of radiation, you can say there is a corresponding linear change taking place with respect to the photoelectric current as well. Okay. So this is the graph that we need to make a note of. So always remember the photoelectric current is on the y-axis. The independent parameter, that is the intensity, is on the x-axis. So what we can say is, since the photoelectric current is observed to be directly proportional to the number of photoelectrons emitted per second, because the number of photoelectrons emitted per second, that is the amount of charge per unit time, is what is called as current. It implies that the number of photoelectrons emitted per second is proportional to the intensity of the incident radiation. Okay, I hope this point is clear. Is it clear, guys?
Yes, sir.
No. The next point is effect of intensity. Sorry, there's the same thing, right? Okay. The next point is effect of potential difference on the photoelectric current. So what are the three parameters I told you? One is intensity, frequency, and potential difference. So what happened in the case of intensity, guys? When you were trying to vary the intensity, what did you keep constant? You kept frequency and potential difference constant. Now what we are trying to do, we are seeing the effect of potential difference on the photoelectric current. right? So what we are supposed to do is, when you're trying to vary this potential difference, you need to ensure that the intensity and frequency are kept constant. So for a given metallic surface C, keeping the intensity I1 and the frequency of the incident radiation constant, the effect of potential difference between the plates on the photoelectric current can be studied. So the figure below shows the variation of photoelectric current with the potential difference V between the plates. Now listen. When the positive potential of A is increased, it is observed that the photoelectric current also got increased. If you recollect, right, there was an evacuated chamber like this, inside which you have a cathode and an anode. This is positively charged, this is negatively charged. So the rays were falling on the cathode, the electrons were coming out. Now what did we do? If you are able to increase the value of the positive charge on the anode, then it was observed that the photoelectric current also increased. The logic is very simple here. Why? Because as you keep increasing the potential of the anode, it will have the tendency to pull more number of electrons towards itself. It will have the tendency to pull more number of electrons towards itself. So more number of photoelectrons being pulled towards itself will give us more amount of photoelectric current. Okay, so what did we do here? We kept the intensity and the frequency constant, and then we did this experiment. Okay, now what will happen is, if you increase the positive, so the question is, if I keep increasing the positive charge on the anode, is the current also going to get linearly increased? The answer is no. So what will happen is, if the positive potential is further increased, right? If you're further increasing the potential such that it becomes large enough to collect all the photoelectrons emitted from the plate C, then the photoelectric current reaches a certain maximum value, and this current is called as saturation current. That is why if you observe the graph, right, anode potential, when you increase the positive value in the rightward direction, the potential is increasing and it is reaching a saturation like this. Okay, so it is reaching a horizontal point. It is reaching a saturation at this point. Right. This current is known as saturation current. Okay. Similarly, if the potential of the plate A is made negative, now the important question that comes. So what is the potential across which C is connected? C is negative. Now what you're doing, instead of the anode having a positive charge, now if you make that also as a negative value, then the photoelectric current does not immediately drop to zero, but what will happen is, but flows in the same direction for the positive potential. See, listen. This shows that the photoelectrons are emitted from the plate C with a finite velocity. So this experiment is like a test. So what are we doing? Basically, anode should have a positive charge, but what are we doing? Instead of giving it a positive charge, if you give a negative charge to it, and you try to increase the negative charge on the anode in the leftward direction, then what is observed is, to a certain extent, the electrons were able to reach the anode. So what is happening? The electrons that are removed, liberated from the cathode are negative. And these charges succeeded in reaching the anode, means they have certain amount of kinetic energy associated with them. But the important question here is, were all the particles able to reach in spite of me keeping on increasing the negative value? The answer is no, because as you keep increasing the negative value, you can observe that the photoelectric current was dropping, and there was a particular value of negative potential on the anode for which the photoelectric current itself is completely cut off. And that negative potential that is used to completely stop the photoelectric effect to take place is what is called as retarding potential or stopping potential.
Sir, I have a doubt, sir.
Tell me.
I didn't understand why it will stop, sir.
Because logically think, no? This is what C and A. C is by default having
Negative.
C is connected to the negative of the battery. Means if the light rays are falling on it, one minute, I'm charging my pins. Now listen. So when the light rays are falling on this, the electrons are coming out, right? So when they're coming out, they will definitely have some amount of kinetic energy associated with it. Are you accepting this point or not?
Yes, sir.
They should have some kinetic energy. Only then they can escape out of the electrical pull due to the nucleus. So when this is happening, now what is the test you're doing? You're actually doing a load test by giving negative potential to whom? To the anode as well. It should have by default had a positive charge. So that positive charge has helped the electrons to get accelerated towards that positive charge. But now what are you doing? You're doing a load test. You're trying to check how many electrons are able to succeed in reaching to the anode in spite of it having a negative charge. So electron is already negative charge. Anode is given a negative charge. What will start getting developed?
So repulsion will be there, sir.
There will be a repulsion. So though this electron has a kinetic energy associated with it, its responsibility is to overcome that repulsion to reach the anode. The question is, will every electron that is getting liberated be able to succeed this kind of a test? The answer is no, because not all the electrons are going to get liberated with the kinetic energy, because it depends on how those electrons are actually coming out, how they are getting knocked out, right? So there might be certain electrons which are able to overcome this negative charge and reach this point because of its kinetic energy, right? But what you're doing, as you keep increasing the value of negative charge, let's say you're taking it to -3, -4, -5, what will happen? Though those electrons, when the charge was -1, it was able to succeed. The same electron with the same kinetic energy will not be able to succeed when you raise it to -5 volt, because the repulsion has increased. It is not able to succeed beyond a point. Then what will happen? When this electron is not able to reach the anode, can you say that the current is cut off?
Yes, sir.
So that's what has happened. That is why we call it as retarding potential. At that point, there is, because all the electrons are getting trapped in between itself. We don't know what is happening to them, but they're not able to reach.
So, sir, even after it reaches the stopping potential, sir, even if you provide more radiations towards C, electrons will not.
But you can't provide, no, because you're not changing the intensity, or you're not changing the frequency. No?
Okay, sir, I understand. Yes, sir.
Right, you're keeping it constant. No? So during the process of experiment, excuse me, during the process of experiment, you're not allowed to change the intensity or the frequency. Frequency means if you're using green light, you should only use green light. You should not change it. Okay.
Sir.
Then what happened? So this is the point they're saying. So if the negative or retarding potential is further increased, the photoelectric current decreases and finally becomes zero at a particular value. Thus, the minimum negative potential that is given to the anode, where is it given? It is given to the anode, not to the cathode. For which the photoelectric current becomes zero is what we call it as cutoff or stopping potential. Okay. So if I take m as the mass of the photoelectric current, the photoelectron emitted with a velocity of Vmax, then the kinetic energy associated with the particle will be half into Vmax square. Right, this is the kinetic energy associated with the particle. This is the maximum kinetic energy I can say. Since if I take the stopping potential as V0, let's say the fastest electron is just prevented from reaching the plate A. So the electron which is having, so there are 10 electrons coming out of those 10 electrons, there will be one electron which is having a maximum kinetic energy. If that electron is stopped, the one which has maximum kinetic energy is stopped, I can definitely say that the potential that we have applied is stopping potential. And if I call that stopping potential as V naught, then the work done by the stopping potential EV naught, because work done by potential is potential energy. We know the potential energy is charge multiplied with potential. So E into V naught is equal to half into M into V max square. Right? This is one of the important mathematical equations that we need to know in this chapter. We keep plugging in the values depending on the requirement, whichever is given. If velocity is given, we will take half V max square. If V naught is given, we will take EV naught. Okay. So the above equation indicates that the stopping potential depends upon the velocity of the fastest electron. Now I think, Rohan, I think you're able to connect all the dots, you will get your answer.
Yes.
So the whole game revolves around the fast moving electron. If the negative potential that you apply on the anode is able to stop the fastest electron that has got knocked out from the cathode, then that potential is called a stopping potential. And what is the mathematical relation between them? The charge of the electron multiplied with the stopping potential is mathematically equal to the maximum kinetic energy, that is half mv max square. Okay. Now what will happen is the experiment is repeated with the incident radiation of same frequency but of higher intensities I2 and I3. So it is found from the graph that the saturation currents are proportional to the intensities of radiation. Means, now what you did is you did the first experiment. This graph is there, no, this blue color graph I'm drawing. So this is the one that is done with a given intensity and given frequency. Now on the same plate, what you're doing is you're trying to repeat the experiment. So try to understand, you're not changing the intensity during the course of experiment. You're changing the intensity only after you have completed the whole process and you start the whole process from the scratch. Okay, when you do that, then what will happen is the intensity of the second radiation, when you increase the intensity, it is observed. What is observed? When you increase the intensity, it is observed that the photoelectric current is directly proportional to whom? The photoelectric current is directly proportional to the intensity. That is why the graph started from here. Because we know the fact, right? Intensity will increase the photoelectric effect or photoelectric current. So if you increase the experiment and try to repeat it, the initial photoelectric current that itself is there for zero anode potential itself will be higher than the previous value. Okay. So when this is getting repeated, then the saturation current will also be slightly higher. Now, if you increase the intensity even more, then what will happen? The initial photoelectric current will be slightly higher. But what is the important point that we need to note here is, if you apply the retarding potential in all the three cases is going to be the same. So retarding potential in all the three cases is going to be the same irrespective of the intensity of the radiation. So that is what is mentioned here. The experiment is repeated with incident radiation of the same frequency but of higher intensities I2 and I3. It is found from the graph that the saturation currents are proportional. Saturation means the ones which are parallel. The saturation currents are proportional to the intensities of the radiation, but the stopping potential remains the same for all intensities. Thus, for a given frequency of incident radiation, the stopping potential is independent of its intensity. A very, very, very important point to be made a note of. So when you talk about the frequency of the incident radiation, the stopping potential is independent of the intensity.
So at the end, the conclusion is stopping potential depends only upon the frequency and not intensity.
Yes, it
And
depends
also
only
the
on the
potential difference.
yes, it depends only on the frequency because we already did two experiments. What is that? We saw how the photoelectric effect will vary with respect to intensity. We got a straight line. We saw how the photoelectric current will vary with respect to the anode potential. You got a graph like this, correct? You got a graph like this. So in that graph, like how you told, it is independent of frequency, independent of intensity, but depends only on the frequency, correct? Now, the third point is the effect of potential difference. Oh, this we already done. Okay. The effect of frequency on incident radiation. The effect of frequency of incident radiation on stopping potential. So keeping the same photosensitive plate C, if the intensity of the incident radiation is constant, okay, you keep the intensity of the incident radiation constant, but you change the frequency of the incident radiation on stopping potential. Like we are going to study what is the effect of frequency of the incident radiation on stopping potential. Okay. So what will happen is intensity is fixed. Right? What is happening? Intensity is fixed. So when there is a light that is falling on a photoelectric material itself, irrespective of what is the anode potential, when for zero anode potential, you can observe a small trace of photoelectric current that is present here. The photoelectric current is still present. Similar is the case here, similar is the case here also. So what is happening in all the three cases? The intensity is the same, but what has changed? The frequency of that material is changed. Means once you are using green, then the second time you are using red, then you are using violet, something like that. Okay. So if that is changed, then what is the important parameter observed? It is observed that higher the frequency of the incident radiation, higher is the value of the stopping potential. Why is it so? Higher the value of the incident radiation, higher is the stopping potential. Because the logic is very simple. C is there, right? So the light that is falling on it will have an energy of h nu. So what will happen is the energy that is given by the photon to the cathode will be used for doing two things. One is to make the electron come out of the valence shell. To make the electron come out of the valence shell, which we call it as, the energy that is required to pull an electron from the valence shell is called as work function. Apart from that, what is happening? The liberated electron should be given a minimum value of kinetic energy as well. Right? So what is this photon doing? The energy supplied by the photon is able to utilize for two values. What are they? One is to make sure that the electron, one is to make sure that the work function is overcome, and the second is to ensure that it is given enough amount of kinetic energy. So if the frequency of the radiation that is falling is more, then the kinetic energy of the particles will also increase. So when kinetic energy is increasing, what is supposed to happen in terms of retarding potential? You need to apply more amount of negative value to ensure that these fast moving kinetic energy, these fast moving electrons are completely stopped from reaching the anode. Are you able to understand? Okay. So for frequencies V2, V3, V2 and V1, the corresponding stopping potentials are in the order of V03 greater than V02 greater than V01, where V0 is the stopping potential of that particular frequency. So it is concluded from the graph that maximum kinetic energy for electrons varies linearly with frequency of the incident radiation, but it is independent of the intensity. So I'll draw this graph and show. This is a very, very important point. So what happens? The maximum kinetic energy of photoelectrons depends on what? It depends on the intensity. Sorry, it depends on the frequency. but it is independent of the intensity of the radiation that is falling. Okay. So if you plot the frequency of the incident radiation against the corresponding stopping potential, you can obtain a straight. Why is it so? I'll explain it. Listen to this carefully. So as I told you, when you talk about an electron in a valence shell, you need to supply some amount of energy, which I call it as h nu, right? This h nu will be utilized to remove the electron from the valence shell. So write it down. Energy required to remove an electron from valence shell is called work function. So the energy required to remove an electron from a valence shell is called as work function. So h nu will be equal to overcoming the work function. Work function is represented by the symbol W naught plus, apart from overcoming the work function, it needs to ensure that kinetic energy is supplied to the particle. So it is half m Vmax square. Okay, but half m Vmax square can also be replaced with EV naught. I told you already. H nu is equal to h into work function can be written as h into nu naught plus E into V naught. H into nu naught plus E into V naught. Okay. Now, what is our job? Draw a graph between the stopping potential and the frequency. So I can write EV naught is equal to h into nu minus nu naught. I can write, or else I can write as h nu minus h nu naught. So E, I will take it to the other side. V naught will be equal to h divided by E into nu minus h divided by E into nu naught. So what is happening? This V naught is Y is equal to this h by E, I will call it as M. Nu I will call it as X plus this whole thing I will call it as C. This is of the form Y is equal to Mx plus C, where C is a negative value. That is why the graph will start from here and its value is given as h divided by E into nu naught. Okay, and this point, at this point, what is happening? When you put V naught is equal to 0, because Y is 0, right? When you put V naught is equal to 0, you'll get nu is equal to nu naught. And this nu naught is what is called as threshold frequency. Any idea about what is the threshold frequency?
Minimum frequency required. So
Yes, it is a minimum frequency that is required to knock an electron from the valence shell. Correct? So am I clear, guys? Any doubt?
So in the third formula, so with h by E into mu, that's V naught, right, sir?
This one, this is, left side is V naught. Right
Okay.
side is nu naught. Okay, nu is represented for frequency. Nu naught is represented for threshold frequency. V naught is represented for stopping potential.
So could you repeat that? Y equal to mx plus u, but how is it related?
V naught is Y because stopping potential is on Y axis. H by E, I'll call it as M. M is the slope of the line. Nu is the frequency. Frequency is on X axis. That is why X is multiplied with M plus C. Is that point clear? So this
Yes,
H divided by E into nu naught is C. Correct?
Yes, sir.
So this H divided by E into nu naught has a negative sign. So negative sign means it should have a negative Y intercept. That is why the graph started below X axis. Okay.
Yes, sir.
So,
Understood.
okay, going forward, let's say they are giving you a question like this. They are giving you the stopping potential, the graph between the stopping potential and frequency. Then the slope of this graph represents what? And the slope of this graph will be equal to H divided by E. That is the meaning.
H here is Planck's constant, right, sir?
H is Planck's constant, E is the charge of the electron.
Okay, sir.
Okay. See, we know that Planck's constant, since you asked, I'm telling you, we know the value that Planck's constant is 6.626 into 10 power minus 34 joule second. Okay. But sometimes in the exam, what they will do is they'll give you this graph. Okay, they'll give you this graph and all other parameters and ask you to find the Planck's constant using this graph. So at that time, what will happen is instead of getting 6.626, you maybe will get a 6.43, 6.34, something like that. Because they are making the Planck's constant as a problem specific thing to verify your knowledge of this graph. So they can ask a question like this also. So if they ask you Planck's constant, what is the important thing that you're supposed to know? You need to understand that the slope of this graph is given as h divided by e. Okay. So from this graph, we can understand one thing. Found that the frequency nu naught, that is the value of the stopping potential, is 0. This frequency is known as the threshold frequency for the photometer used. So from the graph, it is clear. The frequency, the minimum frequency at which the stopping potential is 0 is what is called as threshold frequency. That is another way to define according to this graph. Okay. So the photoelectric effect occurs above this frequency and ceases below it. Therefore, threshold frequency is basically defined something like this. It is the minimum frequency of the instant radiation below which the photoelectric emission is not possible completely, however high the intensity of the radiation may be. You can take any intensity you want, but the minimum requirement for any electron to get knocked out with the energy that you are supplying is that the photon should have a minimum value of frequency called as the threshold frequency for this phenomenon to take place. And logically, what will happen, the threshold frequency is obviously going to be different for different metals that we are going to use. In this experiment, we're using metal. Suppose you are going to use copper, it is going to be something different. You're able to understand this? Right? So these are some important points. Then the next topic that we have are laws of photoelectric emission and other things. Okay. Einstein's photoelectric equation, which is almost like the equation which I already wrote. I wrote one equation today. Did you guys see? H nu is equal to W naught plus half mv square. This is actually an equation of Einstein's photoelectric effect only. So I have covered that part also here. So mathematically, the important parts are covered. So by tomorrow, I can complete this chapter itself. Okay. So is there any doubt, guys?
No, sir.
Okay. So till let's say, let me give you an outline. Listen to this for everyone. Tomorrow I'll be completing this chapter. Atoms chapter 2 more days. So totally I'll be needing only 8 classes to complete your 12th standard syllabus, the remaining chapters. Because all these chapters are very small, maximum number of classes that I require are 2. Nuclei, I require only 1 class to be honest. But since there are some problems, I'll be taking 2 classes. So 2 more means I'll be needing 7 more classes to complete this. And those 7 classes are going to be only at this time. That is from 5:30 to 6:30. Okay. So if needed, I might be taking some extra classes during the week also, maybe on a Thursday and Friday also. So I want you all to be mentally prepared for it, which I can tell only on the ad hoc basis. Okay. Is that clear?
Yes, sir.
Yes, sir. Yes, sir.
Good. Okay. So I'll see you all tomorrow.
Thank you, sir.
Thank you, sir. Thank you.
Thank you, sir.